Lesson: Machine Learning Principles. Machine learning is a critical component of artificial intelligence, underpinning many of its most powerful applications. At its core, machine learning involves the development of algorithms that enable computers to learn from and make decisions based on data. This process is essential for enhancing cybersecurity, as it allows for the detection and mitigation of threats in a manner that is both efficient and adaptive. The purpose of this lesson is to provide a detailed exploration of the fundamental principles of machine learning, their theoretical underpinnings, and their practical implications for cybersecurity. The foundation of machine learning lies in its ability to generalize from specific examples, which is achieved through the use of statistical methods and computational algorithms. The process begins with the collection of data, which is then used to train a model. This model can then be applied to new data to make predictions or decisions. The primary goal is to create models that have high predictive accuracy, meaning that they can correctly predict outcomes for new, unseen data. This ability to generalize is what makes machine learning so powerful and versatile. One of the key concepts in machine learning is the distinction between supervised and unsupervised learning. Supervised learning involves training a model on a labeled dataset where the correct output is provided for each input. This allows the model to learn the relationship between inputs and outputs and to make predictions based on new inputs. For example, in the context of cybersecurity, a supervised learning model might be trained on a dataset of network traffic labeled as either benign or malicious. The model can then be used to detect potentially malicious traffic in real time. In contrast, unsupervised learning involves training a model on an unlabeled dataset where the correct output is not provided. Instead, the model must identify patterns and relationships within the data on its own. This can be particularly useful for anomaly detection, where the goal is to identify data points that deviate significantly from the norm. For instance, an unsupervised learning model might be used to analyze network traffic and identify unusual patterns that could indicate a security breach. Another important principle of machine learning is the trade-off between bias and variance. Bias refers to the error introduced by approximating a real-world problem, which may be complex, with a simplified model. Variance refers to the error introduced by the model's sensitivity to small fluctuations in the training data. A model with high bias pays very little attention to the training data and oversimplifies the model, leading to high error on both training and test data. On the other hand, a model with high variance pays too much attention to the training data, capturing noise along with the underlying pattern, leading to low error on training data but high error on test data. The challenge is to find a balance that minimizes the overall error. Regularization techniques are commonly used to address the bias-variance trade-off. These techniques add a penalty to more complex models to prevent them from overfitting the training data. For example, Lasso adds a penalty equal to the absolute value of the magnitude of coefficients, which can lead to sparse models that are easier to interpret and less prone to overfitting. Ridge regression, on the other hand, adds a penalty equal to the square of the magnitude of coefficients, which can lead to more stable models. In the context of cybersecurity, machine learning models must be robust to adversarial attacks. Adversarial attacks involve manipulating the input data to deceive the model into making incorrect predictions. For example, an attacker might add noise to an image in such a way that it is imperceptible to humans, but causes a machine learning model to misclassify the image. This is a significant challenge for cybersecurity, as attackers are constantly developing new techniques to bypass defenses. One approach to mitigating adversarial attacks is adversarial training, where the model is trained on adversarial examples into the original training data. Feature selection and extraction are also crucial components of the machine learning process. Feature selection involves identifying the most relevant features in the data that contribute to the predictive power of the model. This can help reduce the dimensionality of the data, making the model more efficient and interpretable. Feature extraction, on the other hand, involves transforming the original features into a new set of features that capture the essential information in the data. Techniques such as principal component analysis can be used for feature extraction, reducing the dimensionality of the data while preserving its variance. The evaluation of machine learning models is another critical aspect of the process. Common metrics for evaluating classification models include accuracy, precision, recall, and the F1 score. Accuracy measures the proportion of correct predictions out of all predictions made by the model. Precision measures the proportion of true positive predictions out of all positive predictions made by the model. Recall measures the proportion of true positive predictions out of all actual positive instances in the data. The F1 score is the harmonic mean of precision and recall, providing a single metric that balances both aspects. Cross-validation is a widely used technique for evaluating the performance of machine learning models. It involves dividing the dataset into multiple folds and training and testing the model on different combinations of these folds. This helps ensure that the model's performance is not overly dependent on a particular subset of the data and provides a more reliable estimate of its generalization ability. K-fold cross-validation, where the data is divided into K-folds and the model is trained and tested K times, is a commonly used variant of this technique. The interpretability of machine learning models is an important consideration, particularly in the domain of cybersecurity. While complex models, such as deep neural networks, can achieve high predictive accuracy, they are often regarded as black boxes due to their lack of transparency. This can make it difficult to understand how the model arrived at a particular decision, which is a significant drawback in security applications where explainability is crucial. Techniques such as LIME and SHAPE have been developed to address this issue by providing interpretable explanations for individual predictions. In conclusion, the principles of machine learning form the backbone of many advanced AI systems, including those used in cybersecurity. By leveraging supervised and unsupervised learning, managing the bias-variance trade-off, employing regularization techniques, and developing robust models, machine learning can significantly enhance the ability to detect and respond to cyber threats. Additionally, the careful selection and extraction of features, rigorous evaluation of model performance, and the pursuit of interpretable models are all critical components of the machine learning process. As cybersecurity threats continue to evolve, the integration of these principles into AI systems will be essential for developing effective and adaptive defense mechanisms.